Hello. A week ago, I discovered that two of the exercises of section 1, namely 4 and 5, had no sound. The first one didn't really need it, but the second, uh, I decided to try to dub to record sound and dub it over. That requires that I installed a video editing program. I can't record sound in it. It should be able to do it, but I can't do it. So I have to work a little more to correct it. But well, that's the kind of stuff that happens when we work like this. But let's go to the second exercise of section 3. So by a line, we mean either the projective completion or the line at infinity. Show that a line in the projective space has an equation of that form, and the same line if and only if two triples differ by a multiple. Okay, actually, the theory I read, a line was defined that way. So a line was simply defined by having an equation, being the solution to an equation of this. Now we have to show that it's the completion, and the completion requires the topology, and that must be defined by the affine topology. My God. Well, let's take the line at infinity. Equation, it has the equation z equals 0, and that's of course that form with c equals unity and ab vanishing. So an affine line well, let's go back to basics totally. It's either this form or this form. Vertical line and one with slope a. And that can easily be written this way. So it does have this form, but then there is the point at infinity. Is that the completion of the line? So if we take one like this and then write it in the form ax minus y plus bz vanishes equals naught, and this one, of course, x minus cz equals naught. And then we should choose an affine space where, say, y equals 0, y is naught, now does this make sense at all? And what do we get then? Well, so this, if y is not, then we have this affine equation. A may be 0, b may be 0. Maybe we should rather put x equals to 0. Then the equation becomes y equals bz and cz equals 0. This one is easy. Z equals 0. So that is, we have y is 3, which means it's 1, it's the point 0, 0.1, 0, which exactly fulfills this equation. And what does it mean that it's actually, it's on this line? It's a little difficult to see the topology seen from infinity. Well, now let's take this one. Y equals bz. And then we should have the point at infinity. No, we do have z equals 0. Now the point at infinity. Well, down here it works with x equals 0. And up here, maybe we should take y equals 0 instead. Then we get various points depending upon where we are. This is an embarrassing confusion, really. If a equals 0, all points work. Oh my God. B shouldn't really, the point at infinity should be defined only by A. So 1.A.0, that's the point of infinity, at infinity. So we should put A equal to, and then set x equal to 1. Oh, so y equals 0 only works when a is naught. Hmm, hmm, hmm. What about choosing x equals unity here? Maybe that'll work better. So this is obvious. This is another expression of the line where y equals 0 is, no, not y, oh, so this is the affine space seen from another angle, not z equals 1, but x equals 1. So the way to choose an affine space is to choose one of the variables to be unity, not 0 as I did. So I don't think this really worked to prove anything. It did feel a little worried about it. So we have to choose a variable being unity. And then it's obvious that this line goes through um, 0 point A, naught point A, and that's exactly 1A naught. Now, in the other one here, let's then choose y equals unity. So now the point at infinity, did I notice that anywhere? Um, let's make that blue. So it's 0.1.0. That's the point at infinity, which of course is up along the y-axis. Let's continue blue. So to do that, we set y equals to 0, and then the equation is x equals cz, and on this line we have the point 0, the affine point. So that's the point of infinity. So that was the first one, the line at infinity and the completion of an affine line. And the completion is the topological completion, and it's done by choosing another affine part of the projective space. That was the first. So they determine the same line if and only if the triples differ by a multiple. If is obvious. So if they define the same line, then we shall show that ABC must be the same. So this was part one. So that's what's given. And we have to show that the coefficients are equal. Or rather proportional. So if we eliminate C1, C2 by multiplying this one with C2 and this one with by C1 and then subtracting, let's go black. Then we get A1C2 minus A2C1 x plus B1C2 minus B2C1 y equals 0. They have the same solutions. Every line intersects the line at infinity. We've just shown that, even the line at infinity. So there is a solution at z equals naught. Oh, and there are fine solutions as well, many. I actually wanted this to vanish, this determinant to vanish. And can we use that? It's fantastic. These quite elementary questions. They do require some technique. Well, let's see if we can finish it. If these determinants vanish, that should be a C. Then either one of them are not, one of these vectors are not, or they are proportional. And that's what, so that seems to be a way to go about it. But if we are at the line at infinity, if it's the line at infinity, then this doesn't really work. So let's assume it's in a fine line, then x and y may be proportional anyway. If it's a line of infinity, then this holds for all x and y, so they must vanish individually. So if it's a proportionality, then to use this one, we must use the one with z. This is not really becoming clear at all. So if it's not a proportionality, then I believe we can deduce this, because there are non-proportional solutions here. And then A1 point A2 is parallel to C1, C2. So we'll just stop with that here, because it'll take a while to make it beautiful. I'm not really sure I can do that while recording. Construct a one-to-one correspondence between lines and points with coordinates such that a bunch of points are the same line in the first if and only if the lines correspond to them meet duals of each other. Now, the obvious way to do this is that if we have a line that is mapped to the point ABC, it's a one-to-one correspondence by the last question, and it goes the other way as well. So it's really a one-to-one correspondence. And what should we prove about that? A bunch of points are at the same line in the first if and only if the lines meet at the same point. So it's sufficient to do that with 2 points, of course. So if we have 2 lines and 2 points. Then they must meet at, no, then they must lie on some well-defined line. Which line? Let's read it again. So I kind of did it wrong, didn't I? So such that a bunch of points are on the same line in the first projective if and only if the lines that correspond to them in the second plane meet at the same. Oh, so I did it a little wrong. So these points should lie on the same plane. No, these points should lie on the first, on the same line. There we go. So we have some points here lying on the same line. So we have an equation here where these are coefficients and A, B, C are the variables. And they may have other solutions. They may have a bunch of solutions. And they are all mapped to the lines AIX plus BIY plus CIZ. I'll just write the ideal, not the equation. That's the usual way. And this is naught because the points lie on these lines. So they do intersect at that point. So it's really trivial. It's just a reformulation. So there was nothing special about that. So what we need to finish the exercise is simply to make this very beautiful and systematic. And the problem is to come from these equations. We have 3 equations like this, and then one of them will not be a proportionality, maybe even 2. I guess 2 of them will not be, and then we will be able to show that the vectors are parallel. And since one of them may vanish, of course, but they won't all vanish, so at least one of them doesn't. So that should prove it. But I agree, it's not perfectly done.